So hello everyone. I am Jesh Darfai, and I will conduct today's online session for the computational science in engineering. I hope you have gone through the lectures for the previous week, and today we will solve some of the questions. If you have any doubts, I hopefully this after solving these questions you will get more clarity, and yeah, we'll start the today's session. The first problem is the distance between the two vectors v1 and v2 is. Here the components of the v1 are given. So these 10, 5, 2 are the components of the v1 vector, and 7, 5, 1 are the components for the vector 2. So we'll see the concept of distance for two-dimensional case. So let's say this is x1 and this is the x2 axis, and let's say this point is 1 and the coordinates are x1 and y1. Okay, so we'll say this. Okay, this will okay. I think x and y will be easier to use. Okay, x and y and x1 y1, and this is point 2 and the coordinates are x2 and y2, and let's say we want to find out the distance between these 2 points. We can use the Pythagoras theorem and find out the length of the line. Let's say this from 1 to 2, which is the hypotenuse. Okay, so this length is nothing but the sum. So length square is equal to this distance is x2 minus x1, and this is y2 minus y1. So we can get the length square, the distance square, which is x2 minus x1 square plus y2 minus y1 square, and we can get the length as x2 minus x1 square plus y2 minus y1 square. And if we use the vector notation, okay, so here the point 1, the x1 and y1 was the coordinate for point 1, and for point 2 the coordinates were x2 y2, and we can, let's say this we will denote by v1 and this is v2. So if we do the v2 minus v1, that will be x2 minus x1, let's say I hat, plus y2 minus y1 j hat, or in if we are writing in the vector form, that will be x2 minus x1, y2 minus y1, and vector v2 will be x2 y2 minus v1 will be x1 y1. And if we, this is v2 minus v2 v1, and if we find out the magnitude of the v2 minus v1, that will be square root of x2 minus x1 square plus y2 minus y1 square. So we can see that if we take the vector subtraction and find out its magnitude, that is nothing but the distance. So we have two vectors, we will do the vector subtraction, and we will take the magnitude of that, which will give the distance between these 2 points in which are pointed by these two vectors. Okay, so the vector v1 is 10 5 2, and it is written as row vector, so to make it column it is transpose, and then v2 vector is 7 5 1. If we do v2 minus v1, that will be seven minus 10, 5 minus 5, and 1 minus 2, and that will turn out to be minus 3 0 minus 1. Now if we take the magnitude of this, that will be the sum of squares of the individual component or all the components, so that will be minus 3 square plus 0 square plus minus 1 square, and that will be 9 plus 1, which is square root of 10. So the distance between the points indicated by v1 and v2 vectors is square root 10. Okay, so we can see this is B is the correct option. Okay, so okay, we'll go to the next question. The next question is state true or false all orthonormal vectors are orthogonal. One second. Okay. So all orthonormal vectors are orthogonal. So first we'll see what is orthonormal, and then we'll see also what is orthogonal, and then we can answer it clearly. So let's say there are two vectors a bar and b bar. Orthonormal, so for the vectors to be orthonormal, the magnitude of individual vector should be 1, and also they should be perpendicular. And the next we will see orthogonal. So for orthogonality condition, the vectors, even if they are just perpendicular, that is enough condition. So we can see that orthonormal has to satisfy this additional constraint along with the perpendicular condition of perpendicularity, so or orthogonality. So it automatically satisfies our condition for orthogonal vectors. So we can see that if the vector is orthonormal, they are also orthogonal. So this is true. Okay, this one was straightforward, but you should know about the concept of orthonormal and orthogonal to answer this. So we'll go to the next question. Next question is, if the projection of vector A on vector B and the projection of vector B on vector A are equal, then the angle between A bar or A plus B and A minus B is. Okay, so I will just draw some picture and then we'll see, or we'll solve first and then we'll draw the picture, and we'll see picture also gives the same answer. So let's start with the projection. So let's say if this is a vector, let's say I'll draw it short. Okay, fine. Let's say this is A vector and this is a B vector, and the angle between these two vectors is theta. The projection of B on A will be of, so this length is the projection of B on A, and that we can see that projection of vector B on A vector A is B. So let's say magnitude of vector B is just B, it is B cos theta. Okay, and one more thing is, let's say we have A bar dot B bar that gives the scalar where the dot product will be AB cos theta, and A is nothing but the magnitude of A and B is the magnitude of B. Okay, so B cos theta is equal to the dot product of AB divided by A, and that gives the projection of B on A. Now here we can see that the angle between A and vector B is theta, and what is given is, if the projection of A on B and the projection of B on A are equal. So what we can see is, I'll write projection of A on B is equal to projection of B on A. So projection of A on B, it will be A cos theta because theta is common, and projection of B on A is nothing but this one, B cos theta. So we can say that A equal to B, that is the magnitude of A and B is equal, or they are of same length, vector A and B. Now what is asked is the angle between vector A plus B and vector A minus B. So let's say A bar plus B bar, and if we take the dot product of this with A bar minus B bar, we'll get the magnitude of A bar plus B bar, magnitude of A bar minus B bar, and cos of, let's say, we'll say not theta because we already used it, we'll just say some alpha angle between these two between A plus B and A minus B, the angle is alpha. Okay, so we'll simplify the left hand side, and what we'll get is A bar dot A bar minus A bar dot b bar plus b bar dot a bar, then minus b bar dot b bar. Okay, and if you see the definition of the dot product, definition, a bar dot b bar is nothing but ab cos theta, and that is nothing but even if we interchange b bar dot a bar, it doesn't affect the answer that we are getting. So we can interchange a bar and b bar in the dot product, and it doesn't depend upon the order in which we are taking the dot product. So if we see this term, they both are equal, and that will turn out to be 0. So these two terms uh, we can cancel. So these two will get cancelled, and what we left with, a bar dot a bar minus b bar dot b bar. And if you see the definition, this cos theta, so a bar dot a bar, the angle between a bar and a bar is 0, so that is nothing but the e square, the magnitude square, a square minus b square. And by the given condition, we know that the magnitude of a and b is same, so what we will get is 0, and that is nothing but a bar plus b bar, a bar minus b bar cos alpha, and we can see that cos alpha must be 0, cos alpha is 0, and that what uh, so to satisfy this condition, alpha should be pi by 2. Okay, and one more thing, we'll draw it, the picture for this. So the projection of a on b and b on a are equal. It means there is no bias towards any of them, so we can just draw the two vectors with, let's say, same length. And if we, let's say this is a, this is b, and if we add these two vectors by the parallelogram law, we can find out the addition. Okay, and if we, let's say, perform the b bar minus a bar, so in that case it will be okay. This drawing is not exactly clear, but yeah, we'll see. Okay, so I will draw the a bar exactly of same length in opposite direction. This is rough sketch, but okay, so this is minus a bar, and if we add this a, b bar and minus a bar, we can see that we have got this addition. So this is a bar plus b bar, and whatever we have is b bar minus a bar. Similarly, you can subtract b also from a, but just for ease of drawing, I have made this. Okay, so here you can see that this angle, we can clearly see is 90 degree, and by geometry also you can try to prove that if this angle is 90 degree. But yeah, we'll stop here. Okay, so this is the question. and the angle we found out was pi by 2. Okay, so I hope this is clear. So we'll now move to the next question. So next question is, a 3 by 4 matrix A has rank 3. The column space of A is dash dimensional space inside R3. So first there are this is one of the word, like this is the columns. Two things we should be knowing: one is column space, then one more thing is the rank. What is rank, what is column space, and okay, then we can give this answer. So first of all we will start with the definition of rank. So what is rank? Rank gives the number of independent columns or rows. Okay, so actually both will be the same, so I will write independent rows and columns. Okay, so that is the rank. So you can see it doesn't matter whether we are talking about the column space or row space, the rank will be the same. Okay, and we'll see the column space, so with the example. So let's say I will take the very simple example 1 0 0 1. So this is identity matrix, and let's say we will say this matrix A, or to avoid exact identity matrix I will just give some other value here 2. Okay, so this is the A, and you can see that it has 2 columns. Okay, so this is the first column, this is column 1, and this is second column. And if we write this column 1 separately 2 0, and second column which is 0 1, I will draw this picture for this. Okay, so C1 is 2 0, so let's say this is C1 vector, and next vector is C2, which is this one. And now let's say so there is some other vector, let's say this is the vector, let's say it has the component the x is 3, and let's say y is also 3. Okay, so we can see that this is, let's say, the vector v. It can be written as the okay, so this vector v has 2 component 3 3, and if you see the C1, we have to stretch this C1 by this value. We can do that by multiplying by 3 by 2 to the first vector, which is 2 0. So you can see that this 2 will get cancelled here, and then it will be 3, and then plus 3 times 0 1, and we can alternatively write vector v is equal to 3 by 2 c1 plus 3 c2. Okay, so I will write it again. So A matrix is 2 0 0 1, and we got we have the vector which is 3 comma 3, and what we saw that this vector v can be written as, if this is column 1 and this is column 2, so vector v can be written as 3 by 2 let's say c1 plus 3 times c2, and the alternatively we can write it as c1 c2 times 3 by 2 3, which is nothing but c1 c2 is nothing but matrix A times this vector. So let's call this vector as x. Okay, so we can see that if we have A and if we multiply with some vector, it gives the linear combination of columns of A. So you can see that A has 2 columns, C1 and C2, and after taking this multiplication or if we do the multiplication AX, what finally we get is some constant times C1 and some constant times C2, and we can see that this is, let's say, x1 and this is x2. So what we have here is x1 c1 plus x2 c2. So this is this vector that we have is said that vector b belongs to the column space of A, because the vector we have got by taking the linear combination of the column vectors of A. Okay, so that is the column space where we are taking the linear combination of the columns of matrix A. Okay, and let's say if we got some vector, okay, so we'll just see now the linearly dependent and independent vectors. I will not give exact definition, but we'll just see what they mean when we are saying they are linearly independent, or even we can write the definition that, let's say, this vector v1 v2 and let's say vn are linearly independent. So if c1 c2 v2 and so vn c and vn equal to 0, if there is any such combination, if we find out that for if this condition gets satisfied only when all c's are 0, only if all ci is equal to 0, then they are linearly independent. It means that all vectors we have to multiply with 0, then only this right hand side will be 0. If there is some combination of these vectors that gives the 0, that means they are linearly dependent. So linearly dependent, where some ci is not equal to 0, and even though some ci's are not 0, this condition will get satisfied. Okay, but that is the definition, but we'll see exactly what linearly, like some example with simple example we'll see. linearly independent. And we just saw that matrix A has 2 0 0 1, and here we can see that C1, let's say C1. So let's say this is now we'll say this A1, which is column 1, and this is A2. So C1 A1 plus C2 A2 is equal to 0, and if we write this, what we'll get is C1 into 2 is equal to 0, and C2, or I will write completely. Okay, C1 2 0 plus C2 0 1 is equal to 0. That gives 2 C1 and C2 equal to 0 0, and with this we get C1 equal to 0 and C2 equal to 0. So we can see that these two are linearly independent vectors, and in this case they corresponds to, they are lying along the two perpendicular axes. It need not to be that case always, that the angle of 90 degree is not necessary to be linearly independent. So this is A1 vector and this is A2, and even if let's say the case is we have two vectors like this, you can see that if we take any linear combination, let's say this is vector v1 and this is vector v2, whatever we do with v1 we will never get v2, and whatever we stretch the v2 we will not get the vector in v1 direction until we multiply with 0, because if we multiply with 0 we will reach at this location, which is will be the same, but except 0 there is no c1. So c1 v1 is not equal to c2 v2 except c1 equal to c2 equal to 0. So this is the case, and what we can write from here is c1 v1 plus c2 v2 is not equal to 0, and only it will be 0 when c1 c2 equal to 0. So they are linearly independent, and if the vectors are collinear, okay, so linearly dependent. So let's say we have a vector, this is v1, and another vector, let's say in the same direction, this is v2. So we can see that v2, let's say equal to 2 times v1, or we can say v2 is equal to some constant time v1. We can write c1 v1 plus c2 v2 is equal to 0, and c1 is not equal to 0 and c2 is equal to, let's say in this our case, is 1. So we can see that some linear, when the vectors, for there are two vectors only, so when they are collinear they are no longer linearly independent. We can see that some they, like if you multiply with some constant to v1 leads to the second vector, and that's where this c1 c2, even they are not 0, leads to the combination c1 v1 and c2 v2 leads to 0 value. So in this case the vectors are linearly dependent. Okay. Okay, so the question that we are dealing with here, we understood what is the rank. So the rank gives the number of independent columns and rows, and we saw what is meaning of independent, and we also saw the column space. So column space is the linear combination of the columns, and that we can take using this product. So if we take ax, whatever x may be, that will give the linear combination of the columns and will give the some vector output, and the all possible vectors that can be obtained by the linear combination of columns gives the column space of A. Okay, so I hope this is the definitions are clear. And A is so now the question is, A is 3 by 5 uh, size matrix and it has rank 3. So okay, I will write. So this is, let's say, V1, this is the first, or let's say A will be easier. So let's say this is A1, which is first column, this is A2, which is second column, A3, A4, and this is A5, and it has a rank 3. So you can see that there must be 3 columns. So rank of A is equal to this, and rank of A transpose also will be the same. So there is no difference between the rank of A and rank of A transpose. If you see that, it will turn out to be the same. Okay, the column space of A is, so you can see that this is the column, and if you see the A1 will be A11, A21, A31, because it is 3 cross 5 matrix, and you can see that it has 3 component, and maximum it can represent the 3-dimensional vector. So it can have max possible space it can span is 3, and the rank which is given is 3. So it means that the number of independent columns, so number of independent columns are 3, and these 3 independent vectors, they can span the 3-dimensional space, because, and maximum possible dimension is also 3, which is which agrees, and that's why the column space of A is 3-dimensional. So this 3 is correct answer. I hope this question is clear. Okay, so this question has many concepts. We saw that rank, then what is the rank? It gives the number of independent columns and rows, and next concept that we saw, the linearly dependent and independent and dependent vectors, how for 2D case and 2-dimensional 2 vectors only we saw some examples when they are independent and when they are linearly dependent, and with that we could able to answer the question. Next we will see the question. Vector space V has a spanning set of size 4. The dimension of the vector space V is necessarily dash dimensional. Okay, so there is a vector space, and the spanning set, so let's say the spanning set is nothing but the vectors that spans the space. Let's say this V1, V2, V3 and V4, these are the 4 vectors, they form the vector space V. So let's say we say some vector V, and let's say this vector V belongs to the vector space V. That can be written as C1 V1 plus C2 V2, C3 V3 and C4 V4. Okay, the dimension of the vector space V is necessarily. Okay, so there are multiple cases possible. So let's say first possibilities will Okay, so what all our possibilities are there? So V1, V2, V3, V4, all are independent. So if all vectors are independent, they will span the four-dimensional space. So in this case, the dimension of V is equal to 4. Now the second possibilities. So here all four were independent. So let's say instead of that, three vectors are independent. So if three vectors are independent, in that case dimension of vector space will be 3. Now second, then third, we can say instead of 3 there are two vectors are independent, and that will give the dimension of V is equal to 2, and similarly we can write for 1. Okay, so we can see that the vector space dimension can be 4, 3, 2, 1. So it can be, so it is less than or equal to 4. So this is the correct answer. So I will repeat the question. Vector space V has a spanning set of size 4. The dimension of the vector space V is necessarily. So if we have the vector space V and the spanning set for that, let's say is V1, V2, V3, V4. So these four vectors, the linear combination of these four vectors will, let's say, form some vector V which belongs to the vector space V, and these four vectors can give like different possibilities. So one possibility is this all four vectors are independent. So if all vectors are independent, they can span the four-dimensional space. To give the example, so let's say V1 is, and we'll go with very straightforward example. So this is V1, this is V2, V3 is the another one, and V4 is, here you can see that all vectors are independent, because if we take C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 equal to 0, we can see that C1 is equal to 0, C2 equal to 0, C3 equal to 0, and C4 equal to 0. So these four vectors are linearly independent, and in this case this one will correspond to, let's say, x1 axis, this is x2 axis, this is x3 axis, and this is x4 axis. And with this axis, the unit vectors along this axis, we can define or define any vector in this four-dimensional space. So this is spans the four-dimensional space. Similarly, we can write for second case where three independent vectors will be there. So these three independent vectors will give rise to the three-dimensional subspace, and similarly for two independent and one independent vector. I hope this is clear. We'll go to the next question. Okay, so the next question is state true or false if A is a square matrix with real entries such that the row space and column space of A are equal, then A has full rank. Okay, so we'll start with example. Let's say A is a matrix, and let's say this matrix is M cross M, and this A has element A11, A12, A1M. Second row is A21, A22, A2M, and similarly last element will be AMM. So when we find the RAM, so we'll do the row operations, and after that we got the vector, got the matrix. Let's say A11, A12. The first will be as it is, and after that let's say we reduce this to 1 1. Let's say this, there are some ones till this location, and after that the lower elements are 0. Okay, and this one I will write it in short. This will be A1M. There will be non-zero elements here. This is 0, this is 0, and it will be A11 to A12, 1, 0 will be here, and the last element will be A. This will be R. Okay, I think this one has to be written in more space, or we will write it in the first matrix itself. Okay, we'll write here clearly. So this is A11, A12 dash. This will be let's say this will be rth row, and AR. This will be ERR, and this is also, let's say, R, and this will be, we have, let's say, brought down all the diagonal elements to 1, and this also can be we'll say tilde, because we might have modified this during this process. 0 0, this is A1M, so on. Okay, so this is the rank of A is equal to rank of A is R. So what it means is, so this, there are R number of rows which are independent, or on the other hand you can see that this R columns, they are independent. So anyway, both will be the same. The rank will be same for A and A transpose. Okay, so it doesn't matter where we, like how we compute the rank, whether it is rank based of the A or A transpose. In both the case, the rank will be the same. It will be independent of the A or A transpose. Okay, and by definition, we also, just before we mentioned, it defines the number of independent columns or rows. Okay, so it defines the number of independent columns or row, and that is nothing but the R. And this actual matrix is of size m cross m, and we can see that this whole the number of columns is m. So we can see that the rank is can be, maximum value is m, and in general R can be less than or equal to m. And okay, so we'll come to the question. So if A is a square matrix with real entries such that the row space and column space of A are equal, so I will write that here. Let's say the rank of the row space and column space are equal, because we saw that there is no need to specifically mention the rank of the row and column, because they anyway will be equal. So this statement is the redundant because that will get always satisfied. Then A has full rank. So we can see that this is will be always satisfied and the rank will be always less than or equal to m, but this condition will be always satisfied irrespective of the whether r is equal to m or r is not equal to m. So even this doesn't so even if the rank of a or a transpose they will be always equal, that doesn't guarantee that it is full rank matrix. So this statement is false. Okay, so I hope this is clear. We'll go to the next question. Okay. Okay, so the next question is the matrix B inverse A inverse A B is equal to B inverse A inverse A B is equal to, so we can see we'll take this multiplication first. It will be B inverse and A inverse I is identity matrix. So identity into any matrix will be same as it is. So B inverse B is I. Okay, so this I is correct answer. Also we can write the same expression in different form such that AB we can write together and we can write B A inverse together. And if we can see that or if we use this definition we can see that whatever is there here must be inverse of AB, and we can write this AB inverse AB, which is nothing but identity, because this is the matrix and this is it is the inverse of this. Okay, so the answer to this question is identity matrix. Okay, we'll go to the next question. The next question is, if matrix A is a 4 by 4 matrix, the lower triangular matrix form of A will be. Okay. So first of all we'll see the what all these matrix E3 2 E3 1 E3 2 and in what order they should come to get the lower triangular matrix. So let's say A is a matrix and A matrix we can decompose as lower triangular matrix. So this is lower triangular matrix and this is upper triangular. And I will write the A matrix such that A11, let's say we'll write only 2 by 2 matrix, and then we will generalize this to more high dimensional matrix 1 1 1 2 A21 A22. Okay, so let's say we want to convert this matrix into upper triangular, let's say A11 A12 and A22, let's say some value, and like this form. So what we can do is, let's say we'll try with some we'll try some combinations first and then we'll find out the answer. Let's say we just multiply with identity matrix to A. What will happen? It will not change the matrix. And if you do that, you will get the same thing. Okay, so that is we already know. So let's say what will happen if we multiply with C uh, by some constant here. Or let's say we replace the 0 at this location by C, and we what we'll get is, let's say if we do this multiplication by first row 1 0, that will be a11 a12. We can see that the first row has not changed. The second row will be C times a11 plus a21, C times a12 plus a22. Okay, now what we want is, we want this element to be 0. So we can write C a11 plus a21 is equal to 0, and we will get C is equal to minus a21 by a11. So we can see that this matrix A1, this is 1 0, this C is minus a21 by a11 1. So what it does is eliminates a21. So whatever element is there at this location 2 1, it eliminates. And that's what so this matrix eliminates. So this is do some elementary transformation which eliminates the a21 location or 2 1 location element. So this is known as e21. So similarly, I will write the matrix. Let's say this is 4 cross 4 matrix. So the elements will be a11, a12, a13, a14, a21, a22, a23, a24, a31, a32, a33, a34, a41, a42, a43, a44. Okay, so if I write A here, and first of all I have to get finally upper triangular matrix on this side. So what we will do first is, let's say, eliminate this element. So that will make 0 at this location. So we will get 0 here. So that will be performed by elementary transformation e to 1. Okay, then we will make this element 0, that will be e31. Next we will make this element 0, which will be e41. Next we are supposed to keep this diagonal entries until, or we should not make this element 0. So next we will go to this one, which is e32. Then we will go to this 42, so it will be e42, and then finally e43. Okay, so we can write this a u. The first elimination that we did is 2 1, then we did 3 1, then 4 1. Okay, then e32, then e42, and e43 last. Now if we see this collection of the operation that we perform, So we can write A is equal to E43, E42, E32, E41, E32, E31, E32, E21, inverse U, and this is nothing but the lower triangular matrix that we are looking for, and we'll see which case matches. So you can see that this matches. So we first of all we eliminate the from the first column. So this, you can see this corresponds to the first column. Then we went to the second column, and that is this 2 here, and then we went to the third column, which is this 3 here. So this C is the correct answer. Okay, I hope this is clear. Now we will go to the next question. The next question is, n-dimensional system can have dash number of permutation matrices. So first we will see what is permutation matrix, and once we understand that, we can easily answer this question. Okay, so let's say there is a matrix 1 2 3 4 5 6 7 8 9, and let's say we want to interchange the row 1 and row 2. If we do the identity, if we multiply with identity matrix, we'll get A as it is. But what we will do is, instead of, so it means that if we multiply with identity matrix, the row remains as it is, they don't change. We just now want to change the order. So identity matrix is nothing but 1 0 0 0 1 0 0 0 1. What we will do is, we will interchange these rows of this identity matrix this way, and third row we will keep as it is. And if we now multiply with this matrix to the A, what we will get here is, let's say if we multiply with this first, we can see that the first, this will get multiplied with first row, this will be multiplying with the second row, this will be multiplying with the last row. So only the second row will sustain if we do this multiplication, or we'll get the 4 5 6 here. And similarly, if we do this multiplication, second and third row will get multiplied with 0, and only first row will get multiplied with 1, which is 1 2 3, and the last row will be as it is. So we can see that this and this row, they have been interchanged. So this matrix is one of the permutation matrix. So this matrix interchange the rows, or it permutes the rows. So that is the permutation matrix. If we post multiply, it might interchange the columns also. So the main task of this permutation matrix is to interchange the rows or column based on whether we do the multiplication pre-multiply or post-multiply with the matrix. Okay, so the one thing is clear is that permutation matrix, let's say we'll say the rows of permutation matrix are obtained from identity matrix. So we can see that the identity matrix has let's say we are interested is in uh, let's say how many dimension n, so let's say n dimensional case we are interested in. So for n dimensional case, so in this case the identity matrix will be of this form 0 0, it will have 0, and this will be, let's say this is the first row 1, so which will be 1 comma n. Similarly the second row will be 0 1, this form, and if we go, it will be this n, and there will be like this, there are n rows. Now uh, we can see here that we are taking the combination, or we are permitting these rows to get this matrix, which is permutation matrix. So there are n rows, so let's say we are interested is in permutation matrix. So in this case it will also will be n by n matrix. So this row 1, this is row 2, let's say this is row 3, and so on. This is let's say row 1, this is row 2, this is row 3, and this is row n. So the first row we have this n possible vectors that can, or n possible row matrix that can be placed in the first row. So this can be filled with n ways. Now once we fill that vector, it will be unavailable for the second row. So for second row we will have n minus 1 possible ways, then we will have n minus 2 possible ways, and then finally there will be only whatever vector is left will get its place in the row n. Okay, so the number of possible permutation matrix is equal to n times n minus 1, n minus 2, and till 1. So this might look like x. So this is the, okay, so this is nothing but n factorial. So the number of possible permutation matrix is n factorial. Okay. Okay, so if for the n dimensional system we can have n factorial number of permutation matrix, and this is the correct answer. Okay, I hope this question is clear, and why it is n factorial. Okay, the next question is, for any matrix A transpose A is always. So let's say symmetric, identity, null. Okay, we'll see that A transpose A, if we take the transpose of this, first thing what we have to do is interchange the location and take the transpose. So we will interchange the position, and we have interchanged the position, and we will now take the transpose of each one, or let's say, so first we have to interchange the position and then take the transpose of each individually. Okay, so this will be A transpose, and this is nothing but A. Okay, so we can see that if we have the matrix, so let's say this will say B is equal to A transpose A. So we can see this is nothing but B transpose and this is nothing but B. So we can see that B transpose is nothing but B. So that is nothing but the symmetric matrix. So this is the correct answer. B is the symmetric matrix. Okay. Okay. So that's all for today. I hope you might have got the clarity on the concept of rank, then column space, the how the vectors are independent, and what else we saw today. Okay, we'll start with the first question. Okay, so this one was related to distance, and we saw the definition of distance based on basic principle of Pythagoras theorem, and we saw that if we take the difference between the two difference of the vectors and take the magnitude of that, it will give the distance, and that's how we found the distance between the vector, the points indicated by vectors v1 and v2. We took the vector subtraction and then took its find out its magnitude. The next question is the all orthonormal vectors are orthogonal. So in this case we saw the definition of orthonormal, where the vector magnitudes will be 1 and they will be perpendicular, and by default they will be orthogonal also if they are orthonormal. So this statement whatever was true. Okay, now next question we saw the what is the projection, and then we saw the definition of projection, and based on that we found out the angle between the vectors that were asked in the question, which were a plus b and a minus b. And then this is the picture, by picture I drawn this, and we can see I did not draw a minus b, but I just draw for b minus a and then showed that there is perpendicular angle between them. Okay, so we'll go to the next, we'll see the next, in which the matrix A was 3 by 5 matrix and the rank was given to be 3. So we can see that there are multiple cases, things we should know. One is rank, what is rank, then what is column space, and how it is related to the dimensionality of the column space. Okay, so in this case we saw what is rank, which is the number of independent columns and rows. Then we saw the definition of dependent and linear dependence and independence with some simple example, and what is linearly dependent that we saw here, and then solve the question. Next we saw that there are four we have given, there were the vector space V, and then there is a spanning set of size 4, and then ask what is the dimension of the vector space. Then there are multiple possibilities that whether all 4 vectors will be independent, 3 will be independent, 2 will be independent, and based on that we saw that if all are independent, then the dimensionality will be 4. If only 3 are independent, then dimensionality will be 3, and the number of independence vector gives the dimensionality. So the dimensionality can be 4 or less than 4. So this was the answer. And the next question was based on the rank. If the row column space and row and column space has the same rank, then A has full rank. That one was false, because we saw that by definition the rank of A and A transpose, which is the rank of A, gives the dimensionality of the column space, and then this is give the dimensionality of the row space. So both will be the same, but this rank need not to be equal to m, and it will be always less than or equal to the m, which is the dimension of the matrix, whole matrix. So matrix is m by m matrix, then rank will be always less than or equal to m. So the dimension of the row and column space will be always equal. There is no special thing that is given in the question, so we cannot conclude that it is full rank. Okay, so that's why this statement was false. Then the next question was straightforward, where the inverse of b inverse of a into ab was asked, and we took the two matrices at a time and then found out that it is identity. And in the next question, we saw that what are the elementary operation uh, involved to convert matrix into the lower and upper triangular. So we saw that if we are eliminating the element at this location, 2 1, that will be performed by e21, and um, so e21, this 2 1 denotes at what location the element will get eliminated. And in order to convert it into the upper triangular matrix, we saw that first of all we will eliminate uh, this element, then this element, and this element. So if we are eliminating this element a21, that will be done using e21. Then next operation will be performed by e31, then e41, and so on. And we saw how and then we took this all matrices on the right by taking its inverse, and that will be the lower triangular matrix. Okay, and the last question was, for n dimensional system, how many permutation matrices are possible. We saw that this permutation matrix uh, will have the rows which are similar to the identity matrix but in the permuted form. So for identity matrix there will be n possible rows for n dimensional case, and each row I have written here, and there are n possible weights. So if we are constructing any the permutation matrix which is of n by n, the first row can be filled with n weights, second row can be n minus 1 weights, and so on. So number of possible permutation matrix will be n times n minus 1 times n minus 2 times so on till 1, and that is nothing but the n factorial. So that was the like n factorial was the answer for that question. And then next question was for any matrix a transpose a is always. So it was morely related to symmetric asymmetric situation. So we took the transpose, and then when take the transpose we have to interchange the position and take the transpose. So we interchanged the position and took the transpose, and it turned out to be if we say A transpose A as B, so we took the B transpose, and finally it turned out to be B itself. So B transpose equal to B means the matrix is symmetric, so the B is correct answer. So that's all for today. I hope you might have got some clarity on the concepts. Okay, if you have any questions you can ask me, or you can ask me in the next lectures. So that's all. Okay, bye bye.